Thank you, Rafi, and thank you, IPAM, for hosting this workshop. And thank you for being here and making sure this workshop is a success. Your presence here really makes a difference. And today I'm going to talk to you about neighborhood change. But before I dive into the work, I want to give you a high-level motivation of what I'm trying to do. And the reality is that we design infrastructure, we write down optimization problems, and they impact, at the end of the day, they might impact real people in real ways. If they get deployed, they impact real people. And when we think about designing things, we think about designing them given the current status quo. But the things that we're optimizing for, these are large-scale things. So they have the chance of changing the status quo. And so it's natural that we should account for this in the process, in the decision-making process, namely thinking about the ways people interact with infrastructure and the way infrastructure interacts with people. And so this is a high-level thing that I'm trying to think about. This is work that I did last semester as a postdoc at SL Math on their fall 2023 program on algorithm fairness and equity. And Jian Zhao, who was another postdoc, is one of my collaborators. And this is the outline for today. First, I'm going to tell you about what I mean by neighborhood change. And then we're going to go into the more mathematical aspects of this talk. And so maybe the most clear concept of neighborhood change that we have in our minds is gentrification. We might picture something like this, where you see an old historical building, in this case in Williamsburg, next to a high-rise, high-development, new development next to it. But actually, gentrification goes back to the 1960s. It's a concept that was introduced it's a term that was introduced by Ruth Glass to describe the movement of the gentry, or affluent people, into working class neighborhoods of London. And there's many definitions of it. Here's one definition of it. This is why I put a little star there. It's a process of neighborhood change in which the primary beneficiaries are homeowners and newcomers, as opposed to incumbent renters. The thing that I want to highlight is that it's a process. So what do I mean by process? Something that happens over time. And there's many stages of it, but roughly speaking, what you see is that in the early stages, you might have a neighborhood like that one that is, in some sense, deteriorated, which makes rent affordable. There might be, but nevertheless, there's people living there, oftentimes, who have their own community and culture. And even though the neighborhood is deteriorated, it might have its existing amenities. It might be in a very nice geographical location. It's convenient. But this relative affordability, what oftentimes ends up happening is that people slowly but surely start moving in. Maybe initially because of rent, but then maybe the neighborhood becomes up and coming. And so toward the end, you start seeing more and more presence of large capital. So there's more money flowing in because of people getting loans to buy homes or improve the neighborhood. And there's also ways of government, like official intervention, going from zoning policy. You might decide that this neighborhood is not going to allow high-density construction, or you might have historical designation that protects the neighborhood from any changes in its layout or design. Or you might see improved amenities, in particular for this workshop, transit infrastructure. Transit is one big amenity that affects this process because, well, if you think about transit, it aligns perfectly with things that we've discussed in the past few days around sustainability and around improving access. And so these objectives call for growth that is centered around transit. Okay, so this is a picture of a perfectly normal BART station in the Mission District in San Francisco. And so what these goals would call is, well, you should develop around the Mission because it's a very conveniently geographically located neighborhood and it has good transit service. But what about the people who already live there? This is a picture of a development advertisement in 1880 Mission Street, about 2 or 3 blocks away from that picture, that has been vandalized. And so, it's clear that some people might not appreciate, especially people who live already there, what's happening to the neighborhood. And so maybe the most common idea around the negative effects of gentrification is displacement. So I'll let you look at this illustration for a few seconds. and then I'll tell you more about displacement. So probably the idea that came to mind is people moving out. So spatial dislocation. This could be because of you're just evicted, or it could be that you're not officially evicted, but you're self-evicted in the sense that you are priced out. So this involves moving out of the place where you're living. But there's other aspects, other conceptualizations of gentrification that don't have anything, that don't necessarily lead or imply spatial dislocation. You could be affected by your neighborhood deteriorated. So what that means is that you're displaced in the sense that your neighborhood has been negatively affected. This could be because of patterns of segregation, and for example, redlining. We mentioned that was mentioned yesterday. It could be because of loss of industries. You could have financial pressure. Maybe the neighborhood rents are going higher and you're trying to stay, but now it's a high proportion of your income. And you could be culturally displaced in the sense that if your neighbors moved out, maybe it's not the same neighborhood where you were happy a few years ago. Here's a quote from Freeman and Berkone. Gentrification brings with it neighborhood improvements that are valued by disadvantaged households, and they consequently make rare efforts to remain in their dwelling sites, even if the proportion of their income devoted to rent rises. So that is just to say, usually we think about displacement in the sense of moving out, but there's other forms of a broader sense of displacement that don't necessarily involve moving out.
Sorry, Carlos, quick, the redlining that you bring up, are you referring there to the past, or are you also implying that right now you have sort of implicit effects like that?
Well, I guess when I wrote this sentence, I was mostly thinking about the past and what effects it had in the long term, in the sense of redlining led to certain neighborhoods being disinvested in and leading to the first stage, which was deterioration. Right. But that's not to say that it's not something that implicitly happens now. I don't know. Okay. So here's the technical challenge. This is a definition that I presented, that I'm using. It's a process of neighborhood change in which primary beneficiaries are homeowners and newcomers, not incumbent renters. And it's a challenge because it's not very precise. If you're trying to do something with this, what does neighborhood change mean? What does primary mean? Who counts as incumbent renter? Who doesn't? It's a very broad definition. And that means that data is unavailable, right? Because the moment you try to come up with a more operational definition that you can do a better job quantifying things with, it's very narrow. You're missing out on many aspects of the process. And also, even if you had your own perfect operational definition, the statistics involved are very hard to quantify, because how do you keep track of someone who moved out? Or how do you put a number on cultural displacement? So these are very difficult things to put a number on. And so that means it makes it very difficult to assess the potential impact of different kinds of policy interventions. So what we did was based on this question, like what can we do to get at least a sense of the potential impacts? And so what we did is two contributions, what I'm calling mathematizing neighborhood change. It's just mathematical modeling. And we're doing agent-based modeling. But what I want to emphasize is that we're trying to treat agents as strategic agents. Some people are strategic. That was also a question in a few days ago. But not as mechanical particles. I don't want to put hard-coded rules as to how the agents are going to behave or what their equilibrium will look like. All the modeling that I want to do is around the incentive structures that they might perceive, and then for the agents to, in some sense, learn what is best for them given everything else.
I have a question.
Yes.
One of the weaknesses of agent-based simulation is that
Yes.
basically we the modelers, we play God and goddess.
Yes.
Basically, we basically assign our subjects the behavioral rules that we gods consider the
Right.
beings focal. basically, what kind of, let's say, how do you,
Right.
what type of behavioral considerations
Right.
are you basically?
So I will say this is the next topic of after this slide. But the things that I want to point out is that I am not. This is precisely the point that I'm trying to make with modeling this as strategic agents, not as mechanical particles. The rules are not hard coded. The incentives are. This is of course a modeling choice based on the deep dive into the planning literature that I presented at the beginning. It's a model. It won't explain everything that happens in the real world. But the hope is that it's based on the planning literature sufficiently enough so that you can try to get a sense of the tensions that are driving what we see. But it won't explain everything, as with any model. Given the modeling limitations, then we look at what happens in the long term, and we get some semi-quantitative insights on the empirical equilibrium we obtain based on some experiments. So this is roughly the idea. And there's a paper on the archive as of last week. OK, so technical background. I am not a computer scientist, but I figured I am going to try to do something different. My background for my PhD was mostly in discrete optimization, but I figured I am going to take advantage of this fellowship that I had last semester to study the planning literature and study maybe a tool that might be better fit for the kinds of things that I wanted to do. So all of what I'm going to say is known. I'm applying known concepts from algorithmic game theory that you can find in this book that I read last semester, 20 Lectures on Algorithmic Game Theory by Tim Roughgarden. And the idea is that we're modeling dwellers as learning agents who are strategic about the dwelling side decision making and who learn by repeated play. Yes?
Is this essentially a reinforcement learning type framework? Or?
Ish, yes.
Okay.
So before telling you exactly how this plays out, I need to go take a detour into something a little more abstract and thinking about a single agent. Okay? So we have a cost minimizing agent who's playing a game against an adversary. The agent has a fixed action space A, and this game happens over a number T of time steps. And what the agent has to do is enact a sequence of actions A1 through AT. From that, assuming that's let's say finite action space that they have. And at every time, the agent does the following. They adopt a probability distribution over the set of actions that they could take. They privately sample from that probability distribution. They sample some action that they will enact. Then the adversary reveals some cost function for that time step. So it's a cost that is specific to that time. It's a function that goes from the action space to some number between 0 and 1, 1 being costly, 0 being not costly. And then at that time step, the agent incurs a cost CT of AT. So we think about the performance of the agent. We're just summing over the time steps of the cost given the adversarial function that the adversary gave of the action that they took. So this is how costly it is for the agent to play this game. And there's this notion of regret with respect to a fixed action A. So if you're the agent, you ran this set of actions, then you might wonder, what if I had just played this specific action and just stick to it? So the regret is the difference between how costly your actions were versus how costly a fixed action A would have been given the same sequence of cost functions. It's just this difference. Now, how good a sequence can the agent enact is the question. Well, to think about this, I need to define this notion of expected regret, where you take the regret formula that you saw on the last slide and just normalize it by the number of time steps, the number of times you play this game.
Sorry, why is this called the regret? I still don't understand it. So regret sounds to me like if you a posteriori know what the completely optimal strategy would have been, and you played the non-optimal, then you would have said that's what I regret. But you say regret is the difference in regards to doing something that always does the same. Why is that called regret?
The reason is because essentially, if you try to do something with respect to the best optimal action sequence of actions in hindsight, it's hopeless. The adversary is just too powerful.
Yeah, but we still regret it, right?
Yeah.
But the question is, why is this called regret if you always do the constant, right? Why would somebody regret that?
Any help? He didn't make up the name. This is pervasive in the literature.
Oh, no, I'm not attacking you. But do you know the answer why it's called regret?
I think
I mean, if the stages were independent,
Yeah.
then there is no new information that comes from making a different decision. So if you think about optimizing and if there's no learning from history,
Yeah.
then this is the setting, this is regret as you want to do it.
I
So
see.
think about
Okay.
it in that context, and then it's regret. But of course, it's now being used in a more general context where one should have tougher benchmarks. But as Carlos indicated, the tougher benchmarks you can't prove things with. So this is a mild but reasonable benchmark that you can.
Okay.
And thank you, David, for that first explanation, because I didn't have a good answer, and that is a perfect answer.
Carlos, go ahead.
Yes.
So is to the agent, is it revealed what the other strategy would have yielded, or they can compute?
Yeah, and so this is a thing that the adversary reveals the whole cost function.
Okay.
So it's full information.
So after the fact, you know what you would have gotten. either
Yes.
way.
sorry.
Yes.
Maybe the answer is it is part of the literature, it is standard, but why don't you use the absolute value? So, because here it may be positive or negative.
Yeah.
Okay. I have my answer.
And so this is what's called a no-regret algorithm. It's an algorithm to produce the sequence of actions that you take. You say it's no regret if its expected regret is negligible for all actions as the number of times this goes to infinity. This is what's called a no-regret algorithm. Do they exist? Yes.
And it was called, what are the actions they can take?
Right, so I'll give a concrete example of what this abstract mathematical framework means in the context of this talk. But I do realize, like, yeah, what does an action space mean? You could think of it as just a finite set of options. Do they exist?
Of course.
It's not clear that they do.
Of course, just true. CT is constant, right?
CT?
CT is constant with regards to A, right? Then the regret is always 0.
CT is constant.
Choose an example where C is constant with regards to A.
So you say,
But for all functions, against any
Oh,
adversary.
I
This
see.
is a very special case.
Yeah.
Okay.
Well, they do. Yeah, you can have some regret.
The answer was right. You said no. The answer was right.
It was right, but not for the reasons you thought you were right. They do exist. You might have some, but then it's not enough to mention. They're necessarily randomized. And here's the no-regret algorithm I know. It's called the multiplicative weights update method. And the idea is this of exploration versus exploitation, in that you try things out and you penalize poor performance. Do it quickly so that you don't get stuck in like doing something that doesn't help you for too long, but not so quickly that you don't give yourself the chance to explore. So this is the way, and this is, by the way, this is a well-established algorithmic framework. Like I said, you can find it. All of it is in the Rough Garden book. The idea is that you have some weights for every action that you have. It's a finite set. And for every time step, you obtain a probability distribution by normalizing your weights normalizing them so you get so that they sum to 1. And then you sample some action according to that distribution. Then you reveal the adversarial cost function. And for every action, you see how much it cost and discounted from the current weight, from the latest weight. So for example, if the cost is 0, then essentially it's a good action that you took, so you don't discount your weight at all. If the cost was 1, then you're essentially discounting the weight of that action by 1 minus epsilon. Okay. This simple algorithm is very intuitive, has nice properties, in that you can bound the expected regret with respect to any action. And in particular, if you want to achieve regret at most delta for every action, this is just how many iterations of the algorithm you need to run. Okay, so it has some nice properties. And now, okay, what am I going with this? That was one agent against an adversary. So let's just jump into the multi-agent setting, where now you have n agents. And I'm going to assume, for simplicity, that every agent has an identical action space. So the action space for agent 1 is the same as the action space for agent 2, and so on. I'm just going to call it A. And for every agent j at time t, they essentially play the game that I described before. They keep their probability distribution. They pick an action. They privately pick an action. They reveal an adversarial cost, and they pay the cost of their action. And now here's some necessary notation that is a bit tedious, but I'll need it. Sigma t is the product distribution of the probabilities that the agents have at time t. This tuple, bold tuple A, is the set of actions that the agents picked at time t. And the one with the subscript minus j is the actions of everyone involved except for agent j. So 1 through j minus 1, j plus 1 through n. So you're skipping agent j. So we can think about the time average outcome distribution, where you take the distributions from time 1 to time t. You take these product distributions and average them out. And going from adversarial cost to multi-agent dynamics, as far as the individual agent is concerned, their costs might as well be adversarial. But if you want to model things, you can essentially say that the cost that an agent has is a function of what they do and what everybody else does. Okay? So this is where the modeling comes in. The point of this is that if every agent in the system is running their own instance of their favorite no-regret learning algorithm, and if every one of them achieves regret at most delta for every action, then you converge to a state of equilibrium, of approximate equilibrium, in the sense that no agent has a strong unilateral incentive to deviate unilaterally from the resulting probability distribution. In the sense that if they change whatever action they would have to do based on the sampling to some other action A prime, they cannot gain too much by doing this, namely no more than a negative delta factor. And if you want to make delta very small, essentially you run the algorithm more and more iterations. So, okay, this is where I started with this technical detour. Here's what I mean by the two contributions. Mathematics neighborhood change is a modeling task. I am going to model not strict mechanics on the agents, but rather I'm going to model the incentive structures that the agents perceive because of the actions they take with respect to the actions that everybody else takes. That's a modeling task. And then looking at what happens with the outcome distribution, the delta t, the sigma t, and trying to say something experimental about what distribution looks like. So let's do some mathematical modeling. What goes into this cost function? I put a what there because now I'm going to start making assumptions about what I think should go in here. And I will try, as one should do with mathematical modeling, to not do it based on my own intuition about the system, but rather try to go into the literature and see what social scientists think about this. I'm not an urban planner, but I thought this is important. And so based on the literature, what I felt was important was, okay, of course, housing affordability, access to relevant amenities. I put relevant there because we're assuming that the amenities are liked by every agent. There could be amenities that are irrelevant. Maybe whether there's a school near your house matters to you or not. Maybe you have children or you don't have children, so why would it matter to you? Or there could be amenities that you actually dislike. Here we're making the assumption that the amenities are relevant. Some notion of community ties. People have some preference to be close to people that they identify with. And also whether the housing site is abandoned or in a good state of upkeep. Okay, so now going into the modeling framework, we talked about action space. We can think of the action space now as a set H of potential housing sites. So if you think about it on a network, would be where edges are road segments and nodes are intersections. As an abstraction, you can think of the intersections being the potential housing sites, just nodes in a graph. There's also a finite set of amenity sites. In this picture, they could be in the blue, the little nodes in the blue. There's some distance function normalized from 0 to 1. So if this function takes a pair of nodes and the cost is 1, that means that these two places are really far apart based on the given graph. There's a finite set of residents, in this case, the agents. And for every resident, they have an endowment. We saw the Lorenz curve already a few times. On the x-axis, you see the cumulative fraction of population. On the y-axis, you see a cumulative fraction of total wealth. And so if you have a number of agents that you want to sample, you can just take a parametric Lorenz curve. There's a families of Lorenz curves in the economic literature. You just pick one family, and you can sample a number of different wealths for different agents. RT of H denotes a residence in a housing site at time t. And rho is the number of residents allowed at a housing site, in that particular housing site at any given time. So this, in some way, this reflects zoning policy. So how do we model affordability? Well, we say that a given site is affordable for resident J at time t if essentially if you think it's a 0-1 thing, it's affordable or it's not affordable. So it's a very coarse notion of affordability. And it's affordable if and only if the number of residents at that site who are wealthier than resident J is less than rho, strictly less than rho. Meaning this agent could afford to live there because they're among the highest endowment agents that chose to live in a given site. Amenities. What do I mean by being a score having to do with the amenities? A site is attractive to an agent in proportion to how close it is to the nearest amenity site. So this says, if the amenity site is really far apart, then this distance will be 1. The closest amenity will be 1. And so this score would be close to 0. Conversely, if you're really, really close, then this is close to 0. And so the whole quantity is close to 1. So you get a good score for the amenity axis. Community. What do I mean by community ties? Well, I'm making the assumption that people they have some preference for being close to people who they identify with. And I'm going to assume that a site is attractive in proportion to how similar the endowments of people that chose to live near a site is to their own. So it's a bit of a complicated formula, but this is just saying it's a distance-weighted or closeness-weighted average of the endowments near a site. And so I compare that average with the endowment of agent J. And so if the difference is small, then you get a high score. If the difference is large, you get a low score. I want to highlight an assumption that I'm making here. This is a class-based conception of community. In particular, it neglects everything having to do with ethnicity and culture that do play a significant role in the way people choose where to live. But I'm doing this because you got to start somewhere, and it's something easier to put a number on, based on the Lorenz curve. But I do want to make this clear. Yes?
Just regarding your assumptions, so you're assuming each agent is making repeated decisions about where to live?
Yes, and I'll get to the limitation.
Sorry, guys, can I ask something about affordability as well? So does that mean at each time step, some percentage of the people find that site unaffordable every time step?
Some people might find that site unaffordable, depending on who else chose to live at that site at that given time.
But if you're comparing to everyone else who already is living there, then obviously some percentage are, because you're looking at some percentile.
It depends on how big this number is, right? So if this number is very big, then everyone can live there.
And this ethnocultural aspect that you brought up, right? That some people like to live close to people that are similar to them. Mm-hmm. That's something you neglect because it complicates the modeling, or because it's too hard to model, it's not well understood.
I don't think there's an easy way to quantify that. And quantifying wealth is easier. Because I have this Lorenz curve to put a number to that.
No, right.
Yeah.
Right.
It's a real important detail. It does, and I don't know how to do it.
Okay. So that would be future work.
Sure.
Okay, cool.
For someone else.
Or myself too. Or myself too.
Cool.
Last step, abandonment or upkeep. Again, that's a very coarse model for this. A housing site is in good state of upkeep or not. It's a 0-1 thing. And it's in a good state of upkeep if anyone at all decided to live there. So it's not abandoned. So we designed scores for each of these aspects and came up with this crazy cost model, which I'll explain. So the first and the last aspect of the modeling, affordability and site abandonment or upkeep, I'm treating as catastrophic ways of displacement. So if you have to move out because you're evicted, it's pretty catastrophic. If you live in a place that is in a really bad state of upkeep, then it's also catastrophic. And so if either of these quantities is 0, so you get a bad score, essentially this whole right-hand side disappears, and you have a penalty of 1. It's a very costly thing to do. On the other hand, if none of those is the case, then there are these other concepts of displacement that are still bad, maybe not as catastrophic, a little bit more manageable. And then they go into this term. And so this parameter lambda between 0 and 1 captures how much do you value one against the other. So maybe some people prefer to be close to amenities more so than being close to their community, and maybe some other people prefer the converse. Now to your point that was asked, it's a limitation. I'm assuming two things. By using this technology, I'm using full information. So this is to say, and this is the question you asked, Rafi, that somehow I know how well it would have done had I chosen to live somewhere else. And that's not exactly true. I mean, I guess in some sense you could say, well, you can access to online real estate agencies to get a sense of whether you could have afforded that place or not. That's a bit of a stretch. From a technical point of view, there are reasons why this full information aspect doesn't really matter that much. From a technical point of view, you can relax that assumption. But the really big assumption that this makes is this of repeated play. And so I'm assuming that agents make these housing decisions in a very light way, which is not true. You don't move around the city every day or how many times can you move to a new house?
Sorry.
Yes.
Why did you choose this application setting? I guess what you're developing is something that applies also to other situations where the assumptions may make more sense.
Yeah. So I will say more about this toward the conclusion, but to give you a spoiler, I guess I was thinking of facility location problems, that you place a facility based on maybe some equity objective, but that decision all of a sudden changed your input. And so I was trying to get a sense of how do you go about thinking about the aftermath of my optimization. So this is sort of the motivation. Yes.
To follow up to that, I wonder if an alternative way to think about it might be to look at it as a single decision, but having updating of social influence. So looking at how your peers are choosing locations over time, and then using that information.
Right. So like the end goal that is probably really going to be really difficult mathematically is how do you embed the findings that I'll present into the first part of the optimization? Like how can I anticipate the aftermath of what my decision will have before I make that decision? Yes.
Real quick, back to the repeated play part where you're saying it's not realistic, like how often can you move? I mean, people do move multiple times. I'm wondering if you could just add additional penalty or cost to moving, and then that would sort of model that like a disincentive to move. But if you have to move, you do move, right? I mean, there are people who.
So here's another assumption of this model that I have to go back a few slides, but I'll do it because it's important.
But it depends also on how you define T, right?
It depends on T.
Yeah, what's your time scale?
Yeah.
Sure.
If it is 10 years,
Then it's fine.
Yeah. And the other thing this framework is doing is that you're assuming you start from a uniform distribution, which is not true.
Okay. Okay.
So at best, this model can tell you something about the inherent tensions,
Yeah.
but you should not use it to explain.
Okay. So including that is kind of pointless.
Yeah. I talked about this. Okay. Okay, so now experiments. Semi-quantitative insights. What I did is, well, this is part of Williamsburg, New York. I got this graph from a library called OSMNX. It's a Python library. If you don't know it, you should. It's a really amazing library by Jeff Boeing. You can query any city in the world pretty much and get a graph, Python object to do graph stuff with it. The nodes, like I said, these are intersections, and I'm going to assume that these are housing sites. The edges are street segments. They're weighted by distance. And I went by hand and found the coordinates of every MTA subway station in this particular zip code and map those locations to the nearest node in this graph, highlighted in blue. So these are subway stations. In this setting, I am assuming you have 289 residents because you have 289 nodes. I'm going to test out different density parameters, one agent per node, 2 agents per node, 4 agents per node, and so on. And 2 different values for lambda. Lambda 0.25 means people prefer amenities versus community. Lambda 0.75 means people prefer community over amenities. Again, limitations. Neighborhood change is extremely complex. I hope this is very clear. This is a stylized model with a specific focus. I chose 4 criteria that I wanted to model. These impact the real process, but these are not the sole drivers of the phenomenon. And in particular, they do not explain gentrification in Williamsburg. I chose Williamsburg because I was thinking, OK, I need a city that is, I was thinking, OK, what is a gentrified neighborhood that I know? And also, I need a city that has some non-trivial geographical placement of amenities, in particular transportation, because that's what I'm interested in. And New York City has lots of subway stations. So this is why. Don't go out of this talk and say, oh, I know why Williamsburg is gentrified. Yes?
So what year data do you look at for Williamsburg?
What year of data? Well, the only data that I'm using is just a graph. Yeah. Other than that is stylized. OK, so let's look at results. This is low density. Left-hand side is people value amenities. Right-hand side is people value community. And the color of a node has to do with the expected endowment given the average outcome distribution by that time. These are normalized, so the least endowed places are 0, are in whatever color that is. Sorry, I'm colorblind. I should have done a better job. And 1 means it's very rich. The size of a node has to do with the expected population of that node. And you see that for low density, wealthy people tend to congregate around the amenities, and less wealthy people tend to be pushed out to the periphery. As you run this for 10,000 steps, 15,000 steps, things don't really change that much. And so this suggests that amenities, relevant amenities, plus low density leads to this effect of suburbanization of poverty. So poor people are pushed out, which is intuitive, not too surprising. What about medium density? I'm going to show for rho equals 2, but the results for rho equals 4 are similar, and they're in the paper. At the beginning, you see, again, some suburbanization of poverty. But as time progresses, you start seeing more congregation of medium density around the amenities and more mixing. So what I observe is amenities plus medium density leads to heterogeneous growth, heterogeneous financially growth, because I'm using a class-based conception, near the amenities. What about high density?
Sorry, do you understand why?
Well, because I increase rho, essentially, I'm allowing more people to live.
Yeah, rho is capacity.
Rho is capacity. It reflects zoning density, zoning regulation.
So it's not surprising.
It's not. It's a little bit. I don't know. It's surprising. Maybe it's obvious in hindsight, but what isn't obvious in hindsight?
Okay, sure, fair enough. Okay.
That's crucial. Exactly.
Yeah.
Okay.
So high density things change a little bit. At the beginning, so T5000, you see less wealthy people congregating near downtown and more wealthy people going out. So this is urbanization of poverty. T10,000, so sort of halfway through, you have this interesting thing that if people really value being close to people like themselves, this effect of urbanization of poverty lasts longer. Whereas if lambda equals 0.25, people value the amenities, they sort of self-organize quickly and go near the amenities. But eventually, over time, you have only growth around the amenities, but that is segregated financially. So in particular, if you value more community, you see that there's only one really dark red spot over here versus 1, 2, or 3 over there. People tend to do a better job self-organizing in a segregated way around the amenities. Yes?
Just to refresh what you mean by density, that's how many people you're allowed to congregate in a small amount of space, basically.
Right, this is this row parameter.
Yeah, so a lot of people are allowed to get really close together.
That's right.
Okay.
That's right. So what I read from this is that amenities plus high density leads to a transient state of urbanization of poverty, which is especially true when people prefer being close to people who are as wealthy as they are. But they ultimately lead to segregated growth near the amenities. So these are what I think are semi-quantitative insights into these 4 aspects. Let me conclude. This is where I started. I want to understand the aftermath of the optimization, right? How do our decisions about how to design infrastructure, place things, impact the people who are going to use them, and how will they interact with them? And I finally get to explain this picture. I was in Berkeley last semester, and I was living in a ad hoc studio in a house, in a single-family home neighborhood. And one thing that shocked me is that there were quite a few, in that neighborhood, there were quite a few of these signs that say, let's welcome new neighbors, not new towers. And there's a website address there. So I took this picture, and then if you turn around and walk not that far, what you'll find is the North Berkeley BART station, which is who knows how many millions of dollars cost to build and operate. And as we saw, at least from the experiments, that this kind of combination leads to suburbanization of poverty. And so where am I going with this? I mean, I don't know. I just started. Public decision making does not happen in a vacuum. There are after effects. There are power dynamics, in particular this one. And we might do optimization based on trying to maximize some social welfare function or trying to do certain things. But our hands might be tied in certain ways. And so we can do a nice model mathematically, but it doesn't mean that it will be accepted by the people who are going to be on the receiving end. And so we need to somehow navigate these constraints. And to do it, I think what we need is domain knowledge. I'm not an urban planner, but I try to take a deep dive into the planning literature. Need technical tools. I'm not a computer scientist. I could have tried to use discrete optimization to model this, but I didn't feel like it was a good fit. So I tried to do something else. And most importantly, with any mathematical modeling exercise, especially those having to do with not physical phenomena, but rather things having to do with people, you need to be very upfront about the limitations. And that is my talk. Thank you.